morning. After this amazing intro, we are going to go back to Earth on planet Memory API, because this is what we are going to talk to you about this morning. And we're going to spend 3 hours together. So that's really great because this Memory API is very rich, many patterns to show you, many things to talk about, including performance, memory access, performance, how to write code that is fast. And this is the subject of this talk. So my name is José, and Remi, what is your name?
So my name is Remi. We are from France, you can tell with the accent.
Despite our Belgian accent.
I'm an academic. I work at a university which is at the east of Paris. It's right in the middle, in between Paris and Disneyland. And I'm one of the guys that contribute to the spec of Java, to the Lambda spec, the module, and so on. So currently working on Amber and VarHandle, mostly. I think.
Okay. And my name is José. I used to work at the university also, but I'm now working for Oracle as a developer advocate. Here is a set of links with the content I like to publish on the web. I also contribute on the website that we launched several years ago with the DevRel team at Oracle, which is called dev.java. And because dev.java might be a little too long to type, I also created a QR code, in case you think that 8 characters is too long to type. In your browser, you can't remember that because you're... Okay. We also publish a lot of content on YouTube, including videos. My friend Nicola is doing the Inside Java newscast, which is, I think, every 2 weeks or something. If you're interested in the last LTS version 21 that was released just a year ago, we published a series of videos called the Road to 21 series, which is really interesting. Maybe some of you are already working with 21? Oh, great. That's
a lot.
That's a lot of people, absolutely. 17? That's, I would say, about a third of the audience, maybe less than that. 21, yeah, probably 70%. 11, which was the LTS before that. That's just a few hands. 8. Oh, come on. So all the people that are working on 21, you need to talk to the people that are still on 8. Do whatever you can to convince it. Earlier version than 8, 7 or something? No one.
5.
Okay. Maybe 23 already. Yeah, several hands are working on 23, which is really great. Okay, so that's the kind of content we publish. We also have a blog post on inside.java, and we have a podcast called the Inside Java Podcast. And if you don't like videos, if you don't like audio, if you don't like reading written content, then I don't know what we can do for you, actually. It's kind of lost cause. If you want to connect and have information about new stuff, about really on-the-edge stuff, the website you need to visit is the openjdk.org website. You have a dedicated space for all the projects currently being developed on the OpenJDK, where you will find the mailing list, the documentation, the wikis, etc. If you go to the jdkjava.net website, you will even be able to download early access versions of several branches of several of these projects. And I would like to highlight the VarHandle early access version, which has been updated at the end of last July, so it's a very recent version. So if you want to play with value types, with implicitly constructed types and non-nullable types, you can do so by downloading this. This is something that is coming. It's not even a preview feature or an incubator feature, but at some point we will have it, and you can already get a glimpse at what it is exactly.
Yeah. Soon.
Soon, yes. Soon, absolutely. You can also check out the Loom early access version, where you have a fix if you're aware of the spinning issue on the synchronized blocks. Well, there is a fix in this Loom early access branch of this spinning issue that you can test if you want to do so. All right, but we are here, and by the way, you already have an early access version of JDK 24, right? So if you want 23, maybe you want to check that. But we are here to talk to you about the Panama project. The first preview of the Panama project was actually an incubator version made available in the JDK 14, and it made it this foreign function and memory API, made it as a final feature in the JDK 22. So that's 8 version because we have 2 versions every year. It means that there were 4 years between the first incubator and the final release of the API. And that was so last March, about 6 months ago. And this is why we are now talking about it. So we are not going to talk about preview features. We are really going to talk about something that you can do if you're working with the JDK 22 or the JDK 23, of course. Every kind of information, wiki, documentation, mailing list, if you see bugs or have feedback or want to get comments, provide comments or do anything, you can connect to openjdk.org/project/Panama, which is the page of the Panama project.
Yeah, the Panama project is not fully done. At the end of the talk, we will talk about several ways it can the API can be enhanced, and yeah, the Panama project had not be delivered fully.
Yeah, there's still more things to come in the future. And I would like to try to first show you an idea of what we're going to show you. Actually, I'm going to switch to the IDE. And believe it or not, but this is an IDE. All right, so I have a file. It's an, I think it's 12 gigabytes or so. With, I don't know if you remember this challenge that was published about a year ago by Gunnar Morling called the 1 billion row challenge. So this is inspired by this challenge, but it's not a text file that I have, it's a binary file with an ID, a temperature, then one more ID, one more temperature, and this, I have a billion of these couples, ID temperatures in a file. So that makes it, and it's not float, it's float. There is obviously a typo. Sorry for that. And I'm going to read this file. So this file is this one. It's on my hard drive. This file is this one. I'm going to read it. So all this code is some Panama code. I'm not going to go through it now because we are going to explain this code along this presentation.
Yeah, bit by bit.
Yeah, exactly, element by element. First, I have a struct layout, which describe actually the way the data is laid out in the file. Then I have 2 VarHandles. VarHandles are a way to access this data when it's loaded in memory.
A structured way to explain to the VM how to access it fast.
Exactly. I have this arena object that is there. Okay. This arena object is this magical object, and we're going to explain you how this object is working. Then the read channel, which is a file channel, the good old file channel from Java NIO, because Panama works with NIO. So I first check the size of the file. Okay, and I'm going to measure the time it takes to process it with this stuff. I'm going to count the elements, ID, the temperature that I have, and then I will just do some processing on it. So first I'm counting the cities. Then I have this nifty, as you can see, stream pattern, and we're going to go through that because you can use the stream API actually to access memory segment in a very efficient way. So here I'm counting the cities, and then I'm going to collect some statistics on the temperature. So I'm not going to go through everything, but as you can see, this is a parallel stream, basically. This element is actually written in a stream, and this is some stream code that you have here with a grouping by and stuff. You just need to be careful because there is 1 billion temperature, so you cannot call toList on that because it will create a list with 1 billion elements, and then it will not work. It will probably even crash this machine. So I'm just going to run this code and show you what it gives. I have 1 billion elements. I'm running on Java 23. Okay, so it's going to analyze all this. It first loads the file. Oh, it's already done. Yeah, this is not what I wanted to do, obviously. So it first loads the file in memory, and then we'll analyze this file with the stream API and with parallel streams. So you cannot hear that, but the fan of this old laptop is kind of spinning quickly now. And you can see that actually analyzing, going through all these files takes between 3 seconds and 6 seconds, .5, when it's loaded in memory. So in this amount of time, you can actually, using the stream API and parallel streams, analyze what you have in this file. Now, I have also a second version of this file, which is structured in another way. This time it's structured in that way. Instead of having int float in float, which is actually a float, I have an int, then the number of temperatures that are related to this CTID, and then the array with the float elements, which are actually float elements. Okay. Obviously, there's a problem with the copy paste. So you can see this second structure as some kind of hash map, all right, created and inline within the file. It makes the file smaller. There is the same information in it, but structured in a different way. It makes it smaller. Creating this file takes some time, obviously. It's not that long. It's about 30 seconds, but I'm not going to do it right now. What I can, the code is here, so when you download the code on the GitHub, you will have it. It's a little hairy code because, well, for some reason. And now this is the code, same kind of stuff, layouts, VarHandles, stream API, etc. But with this reorganized structure, now I can process the file in less than 1 second. Okay, and also with the parallel stream, with this summarizing int stuff, I can collect actually the count, the sum, min, max, and average automatically for each city. Okay, so this is what this code is doing. So you can see that with the memory API, you can load files that are far beyond what you could do with the previous Java NIO API. You can process that with a very clean API, which is a stream API, and in a very efficient way, because processing billions of elements within seconds is actually pretty efficient. Okay, so let me go back to the slides. And this is not what I wanted to share with you. Okay, now let's talk about the goals of Panama.
For a long time, Java was afraid of C. That's why I don't know if you remember, if you are old enough, there was some campaign about being 100% Java and things like this, because at the beginning, people didn't wanted Java to become like Python, which is each time you have a problem, a performance problem, you start to write the code in C and you just have a wrapper on top of it. So for a long time, the only way to access C code was to use GNI, and because GNI is just a pain to write.
Wasn't GNI updated with the JNA at some point?
Yeah, so you have library on top of GNI that exists, like GNA and GNR, that soften the pain, let's call it that way. But now Java has grown up quite a bit since the early days, and Java is not afraid of C anymore. And now that we have JIT, basically what Panama is to try to tell the JIT how to access C code, C function, C data structure, and so on. So the Panama is called, by the way, Panama because it's the rift in the isthmus in between North America and South America. So trying to heal the rift between Java and C. 20 years ago, a nice library called Java NIO, perhaps for new I/O.
It was called new I/O at the time.
Yes.
It didn't last very long, but never tried to call an API new something, because at some point It will not
soon
work
it will
anymore.
be not new anymore. And so one of the things, there are several shortcomings with the ByteBuffer API, and one of the things that Panama does is to upgrade the ByteBuffer API. So we'll show you what are the shortcomings and how they can be solved by the memory API.
So you said 22, that's actually 22 years ago. It's more
Yeah,
than 20
yeah,
years
a
ago.
long time ago.
So what was new in Java 4?
So yeah, let's let's pretend we are in 2002. What are the nice feature of Java 4?
I need to dye my hair.
So obviously in 2002 XML is all in. It's like the AI of 2002. So we have a new XML parsers. We have exception chaining. You can have an exception and wrap it into another. Huge progress. And the main feature of Java 4 is the new input-output API, which was GSR 51, which is one of the major GSR at the time. I mean, it was a way to show the community how we can work together to deliver something. Because before it was mostly Sun doing things internally, and this is one of the first GSR that was published with a public expert group from coming from different company. So it was a milestone, in fact. So in 2002, we have obviously one browser. It's far simpler, apart the fact that it's Internet Explorer. And
Who remember these glorious days? Oh my God.
okay,
Here you
all
go.
people in the room.
We were called J2EE architects at the time.
Yes.
I remember that.
Yeah.
That was something.
And by the way, we had some kind of Ajax thingy that was Microsoft proprietary at the time, and you can just access to your Tomcat thing. So before Java 4, if you had a servlet and you want to write things on a socket, basically your web server had to copy the data from the heap memory to the native memory, to the C-like memory. And with the new Java NEO API, now with the ByteBuffer API, you are able to allocate memory directly into the native memory, so you avoid a copy each time you do a read or a write. So it's
better and faster.
it's fast. It depends on the size of your buffer, obviously, but for web for things like Tomcat and so on, it was really important at the time.
When you have 20 clients a day, you don't have any memory
Yeah,
performance issue anyway, so that's perfect.
So how to create a ByteBuffer? You have two ways to create it. One is to call allocate direct, which is basically direct means native. And you allocate the bytes directly using malloc. This is what the Java calls does. Or you can wrap a file in memory using a file channel, and you have a nice map method. And one issue with this API is that a ByteBuffer is limited to 32 bits. So when you allocate with allocate direct, you have an int in parameter. when you map a file, you have longs, but the size cannot be more than it has to fit in a 32 bits int.
Which is not that bad because in 22, 3.
Yeah. I mean, the
24.
Hardware was not able to.
Yeah, 32 bits was the max size of your operating system, anyways.
Yes. Yeah. And technically, it's 31 bits because you have one sign bit.
So it's
So not more than 2 gigs of RAM can be accessed.
So let's talk about the ByteBuffer issues. And by the way, we have a demo on that. So let me show it to you.
Yeah, one of the issues is that you have some known issue with the ByteBuffer API, and you have some
less known.
Let's say like this, less known things like it will work, but you will have no performance.
Yeah. So by the way, I'm using this nifty feature that is a preview feature of Java 23. You see that this is a class, but I didn't have to write public class, blah, 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 all this ceremony. The compiler is able to do that for me. And I'm also using a simplified version of the main method, which is just void main without the public, static, etc. And the println here is not system out println. There is no import in this kind of class. It's actually taken from an IO class, which is imported by default when you're using this kind of technique. So yeah, it's nice to have that. So here I'm basically allocating a ByteBuffer of heap with 512 elements in it, and I'm just putting 42 at the place 4 and reading it, and it's going to work. And that's basically one of the patterns you have to use ByteBuffers, which is very simple. You can use ByteBuffers to write files. So here I have a text block there, and I'm going to allocate a ByteBuffer with 64 elements in it, and I'm going to put this string of characters in UTF-8. And if you do that, you just need to remember that you need to flip your ByteBuffer. ByteBuffer works with an index, and once you've written to your ByteBuffer, if you don't flip, you know what? I'm going to comment this line. I'm going to delete this file, which is file2.txt, run this code, and if you just write the ByteBuffer to the file, actually what you're writing is between where the index is and the end of the ByteBuffer, right? So if you open file2.txt, you have null elements because you forgot to call this buffer.flip. Now if I call buffer.flip and suppress this file and run it again, now I have hello ByteBuffer, and if I open the file, I have hello ByteBuffer. This is kind of a little weird. I know that people who are playing with ByteBuffers at the beginning, they really need to remember this kind of thing, which is not always easy.
Yeah, so the ByteBuffer API is not only memory, it's a bunch of index to say, I want to see this memory when I do a read or when I do a write.
But this is how the API has been designed, and I would say it's kind of okay-ish. All right. But there are other issues that are a little more annoying. So this code is basically the same kind of code. I'm now writing hello file mapping in file3.txt. And you can see that here I am just getting this new array, and I get the content of the ByteBuffer in this array, so I can read it, and I can put directly in the ByteBuffer a carriage return in the middle of the string of character. So if I run this code, you see that I actually read hello, and the file content is a hello file mapping with this carriage return in the middle of it, and I should have it, by the way, also in the file. So actually, because this array is a mapping of the file in memory, if I modify the array directly, it will modify also the file that is that it is mapping. All right. So this is the basic pattern to map the content of a file in a byte buffer, and we're going to do the same with memory segment and the memory API. So this is why we're showing that to you. But the problem with this is that if I take, by the way, I could take all this. Let me just take this, and I put it outside. Oh, yes, I need to take the array too. And if I'm putting it outside of this try resource statement, so now take a close look at what I'm doing. I'm opening a file. I'm creating a byte buffer that is mapping this file in memory. And I'm closing the file here because this is a try resource statement. So the file is closed when I exit this try block that is here. All right. So when I'm here, the file is closed, but I still have a reference on the byte buffer because this byte buffer was created. Well, the variable was created there, and the byte buffer was initialized there. All right. And then after the file is closed, I'm writing and reading from this byte buffer. So what would you expect to happen? Well, it would be nice, since the file was closed, that this code would crash, right? But the problem, is that not only it doesn't crash, but it is still writing in a file, even if this file was closed. So that's one of the issues that I would call that a hidden feature. Okay, of the byte buffer. But the problem is that if I wait for a long time, maybe it will crash in the future. All right? Who loves to have random bugs in your application? Yeah, I think we all agree on that. So that's one of the issues of the byte buffer. You can map a byte buffer to a file, close the file, but still use the byte buffer for a certain amount of time. And of course, this is not specified. So
yeah,
you're on your own.
Basically, you rely on the GC unloading and mapping the file. But now that we have nice GCs, they tend to don't reclaim memory, some part of the memory that is not under pressure, which means that the byte buffer may never be unmapped.
Exactly.
So if you have a server, at some point you will run out of resources because you have no control on when you can unmap.
And that's this demo, by the way. Here, I have my byte buffer class, which is just this one, and this wraps a byte buffer, and this buffer is actually registered to a cleaner. So the cleaner is some kind of mechanism that mimics the finalization mechanism that, by the way, is going to be deprecated and removed from the JDK at some point.
You mean the finalizer, not the cleaner?
Finalizer, yeah. Yes, the finalizer, the finalize mechanism that calls your finalize method in your classes is going to be removed. So if you have code in the finalize methods of your object, you should definitely do something about it, because at some point in the close future, it will not be called anymore.
Really close future.
Yeah, really close future.
Soon.
But sooner than Valhalla.
Sooner than Valhalla.
Yeah, it will happen before Valhalla. So you have this cleaner API, which is an alternate API. Basically, what you can do is that you can register any object to this cleaner. You could see this cleaner as some kind of queue, all right? And you register a runnable, this object here, well, this lambda here is a runnable. You register a runnable that can do something when your object will be reclaimed by the garbage collector. The difference between the finalize method and this runnable is that this runnable cannot get a reference on the object that is going to be reclaimed, because when the JVM calls this runnable, then the object is already not in memory anymore, kind of. All right. Whereas when you call the finalize method, because you are calling a method on this object, the object is still in memory. And if within the finalize method you say, oh, I'm going to take the object I'm in, and I'm going to put it in some kind of static hash map or cache or whatnot, then this object cannot be garbaged anymore. So calling finalize can actually, mess up with the way the garbage collector is working, and it does in many cases. So here the cleaner API doesn't do that. But you still have some kind of callback when the object is reclaimed. And you see that here I'm allocating a byte buffer of 8K. and then I'm putting this variable to null. So this ByteBuffer is not referenced anymore. But if I run this code, because there's absolutely no pressure on the memory, the GC will never do its work, and it will not reclaim this ByteBuffer. Actually, this ByteBuffer is in the memory. Okay, so I have 8K that are lost because I don't have any reference on it anymore. But because the GC does not clean this ByteBuffer reference, that is null. Well, this ByteBuffer instance, sorry, because the reference is null, it could do that, but because there's no memory pressure, it will not do it. And then you have a memory leaking in your application. So that's embarrassing. If I explicitly call the garbage collector, then you will see that the cleaner message that I put is called, and the ByteBuffer has been freed. Well, the off-heap memory segment ByteBuffer segment that I created was cleaned. And this is really an issue because it means that all the ByteBuffer that you create, they're actually consuming memory in the off-heap part that is not managed by your garbage collector. But if you don't have any pressure on your on-heap memory, these objects will never be reclaimed, and thus your off-heap memory will never be reclaimed neither. So you may run out of off-heap memory just because you don't have any pressure on your on-heap memory, which is really an issue. Okay, so we are going to see that the memory API is fixing this issue.
Yeah, the other problem, which is a lesser problem, is that register calling cleaner.register is not that free.
Yeah. So let me go back to the slides. So these are the issues with the ByteBuffer API that you want to fix, that are fixed actually with Panama. First, the memory access API, the ByteBuffer API is a little too high level. You have all these indexes that are not easy to handle. It is only for 32 bits indexing, and if in the early 2000s it was not an issue because most of the operating systems were 32 bits, now it's not the case anymore. Everybody's working on 64 bits, so that's really a limitation. It also allows for unlined access. We have not talked about that, but we are going to talk about it in a minute. But the biggest problem is that the deallocation is undeterministic. And this is, excuse me. And this is really an issue that needs to be fixed, and that is going to be fixed. Okay. Currently, how is the deallocation is working? It all relies on the GC. The GC will select a region that contains your ByteBuffer reference. Then it will see that the ByteBuffer is dead, and the cleaner code, which is a requefont, will push that to the cleaner queue. And later at some point, the cleaner code will itself call the reclamation of the off-heap memory. And as I showed you, if there's no pressure on the on-heap memory, it's not going to work. So the Panama API actually brings a new API, which is called the MemorySegment API. And this MemorySegment API does solve the same kind of problem as the ByteBuffer API, but fixes all these issues and brings some more features that we are going to see.
And some more issues.
Some more issues, as always. So what is a memory segment? First, it is something that is safe. If you map a file to a memory segment and you close the file, then you cannot use the memory segment anymore. Okay? So there is an incompatibility with ByteBuffers, but a welcome one, I would say. It gives you the control over allocation and deallocation. By API, you can explicitly deallocate a memory segment. Okay, so that's the second fix. It brings performance because, as we are going to see in a minute, there is already an API that is kind of doing the same, which is called unsafe. Any of you are using unsafe? Not that many, just a few hands. All right. So many people are using unsafe because it gives you good performance. So the memory segment wants to bring a replacement to this unsafe class that is unsafe, as it is called. So this is something that needs to be done also. It also offers direct access and index access. That is, either you want to access this piece of data at this offset, or use something that is an array-like access. And by the way, also a stream-like access. If you want to do some unsafe access, like accessing at the direct offset and the length, you can do so, but you know that it is unsafe because the API tells you that.
Yeah, it's something which is funny, which is the memory segment API let you access to an unsafe part of the memory, but you have to ask for it. You have to ask for the unsafe API. So we are not removing all unsafe API. We are creating a new unsafe API which is not SunMISC unsafe.
Yeah. And which is not as unsafe.
Yeah, it's less
Kind of.
unsafe. Kind of.
And it has to, and it works also with the ByteBuffer code. So if you have legacy code that is using ByteBuffer, maybe it's not legacy code by the way, then you can also play with the memory segment API because it has been designed in that way.
It's something which is important. It's not an API which is at the same separate or at the same level. Yeah. It's a low-level API, and the ByteBuffer API was rewritten on top of the memory segment API.
So just a few words about SunMISC unsafe, because this class is going to go away at some point.
Really go away, removed.
Yeah, so you will try to compile and tell you, oh, this class does not exist. No class def found error. So that. The nice thing is that it's close to the C performance, which is also the case for the memory segment API that we're going to use. The less nice thing is that you don't have, you can still access something that has been, a piece of memory that has been freed, just like the ByteBuffer that you can access when the file is closed, right? Which is not the case with memory segment. There is a protection against that. So it means that you're really in an unsafe world, and you can easily write bugs that may crash your application or not, depending on what you're really doing.
And crashing is not really the issue. The main issue is but usually when you have a use after free, it doesn't crash until you call another malloc.
Yeah.
So usually it works, but it's a real security issue
because you're reading a piece of memory that you're
not supposed. Yeah. You don't own
that
anymore.
Was written by someone else.
And someone can weaponize it.
Yeah, absolutely. You can pick and poke everywhere. So with the segment API, you cannot do that, but in a controlled manner. There is no null check for on-heap array access. And that
it's really unsafe.
May crash or may not crash. And just as a side note, the memory access methods have been deprecated for removal by the JEP 471. I don't have the dates, but that was several years ago.
Yes.
Yeah. And you have been warned that it's unsafe since 2006. That was 18 years ago.
And it's not a removable warning. You cannot suppress this warning.
And this is your demo.
It's my demo.
Which one do you want? The USB-C or the HDMI?
Yeah, USB-C.
You know what? I'm going to give you both.
Okay. Do the magic.
Yeah.
Yeah. Can you read it? Yeah.
Yeah.
So this is how you can use a memory segment. So you allocate it. It's always off-heap. There is no allocate direct if you prefer everything. If you're using an arena, we will see what an arena is. But it's basically always on-heap, off-heap, sorry. We have a kind of a global things, which is this part will never be deallocated. So it's a kind of immutable memory. You can print segments if you done this kind of things. The segment will give you the real address in memory. Yes. So you can debug it, because with a ByteBuffer you'd have no way to print basically where you are. You are just alone in the dark, which is kind of sad. So you have two ways to access to the memory segment, which is basically the two ways a CPU, what the CPU gives you, which is you can access a direct offset by the method set or the method get, and you will first provide what is the kind of layout I want to read. So here I want to read Java int. We will see later that you can ask for reading a C int, by example. And so you have an offset, which is a long, not an int, and you have the value, something which is kind of weird, is that if you access to an offset which is not a multiple of the size of the data you want to access, so here I'm trying to access to, to 3 here, it will gently crash because most of the CPUs don't allow unaligned access. So the way it works with ByteBuffer is that you will get several read, and it will reconstruct the int. So basically read 4 bytes and reconstruct the int, but you lose performance. So it's better to just say, don't do it. The CPU doesn't support it. I mean, if you are using the memory segment API, you want something which is fast. So if you want something which is fast, it should crash if there is no way that the CPU provide you this API. So actually, it's a good exception. Don't do that. And so you have the get here, and you can do the same thing with set at index and get at index. And in that case, as the index will be multiplied by the size of the layout to find the offset. Basically, you have these two access because this is what a CPU provide. So it's a really low-level way to see a memory segment, which is you have the guarantee that it will be mapped directly to one assembly move if you're on Intel. That's all for this first demo. You have some nice set string and get string that are nice and not that nice because you are interacting with the C word. So it works with the C convention, which means that you have to have a /0 at the end. If you set the string, it will append a /0 at the end. And if you get a string, it will pass until there is a /0. So if they are not /0, good luck. So yeah, it's far lower level API than the ByteBuffer API. It's really a way to interact with the C world. If you want to use a memory segment to write something on a file, actually you can't. You have to have a ByteBuffer as some way, in the middle, which is because the memory API is more low level. If you want to read or write, you have to use a ByteBuffer. So this is one of the things which is currently discussed in the Panama mailing list, which is should the I/O be add more methods that take memory segment as parameter. But currently this is not the case. So if you have a memory segment and you want to write something, you will have to call as ByteBuffer. And as ByteBuffer is a view of the memory segment. It will not create a new memory segment or something like this. And play with the limit thingy, like the flip, and then being able to write in it. So you can allocate a byte buffer directly in memory, or you can wrap an existing array and see it as a memory segment. The other thing is you have a copy method that will be able to copy from one memory segment to another memory segment. There is something funny, which is there is only one copy method. You don't have a copy method that will take parameters and be able to copy one part of the memory segment to another part of the memory segment. If you want to do that, you have to slice your memory segment first. So you have a slice method that will take one part and then call copy method. And the VM will optimize everything. The interest is that if you have a slice, basically you say to the VM, now the size of the memory segment I want to see is this. And it will help for when the VM will optimize the whole thing. So yeah, this is the way if you want to read or write. And the recommendation is to use a temporary byte buffer, because it's just a view and the VM will be able to see through it and not allocate the byte buffer.
You mean the
relying on the escape analysis
of the byte buffer class, the object itself?
Yes, the object byte buffer itself will not be allocated if it's a temporary object, which is if the VM is seeing when the byte buffer is created and the last time the byte buffer is used. It can be removed using escape analysis. So currently, the memory segment, you may have some trouble with that because it's relying on the escape analysis, which means that you are not free to create with as byte buffer a byte buffer and then sending it to a method, because it may trouble the escape analysis. But with Valhalla, this kind of object will be tagged as they will never escape, and you will have the guarantee that the VM will optimize it soon.
When Valhalla comes.
When Valhalla comes. When it will be a preview, it will be enough.
That's the demo for later.
Okay, you haven't seen it.
Oh, you will see it in a minute, don't worry. So we just talked about alignment. Now, how is this going to work? That's going to be interesting.
Maybe not.
Oh yes, it did work. Amazing. So the alignment is the following. Here is a piece of memory from the address 00FFA and 3 zeros. Right? You can align bytes on any address, but a short, which is 16 bits in Java, it's not the case in C, can only be aligned to even addresses, as you can see on line 2 and 3. And the int, which is 32 bits, can only be aligned on addresses that are divisible by 4. All right. It does not mean that your CPU will not be able to read it, but it means that it may read it with lesser performance, like multiplied by 2, the access time I'm speaking about, if you try to align them in that way. So in the memory API, you can actually detect that, and we'll see this technique of adding padding bytes to make sure that all your data is properly aligned, especially when you are dealing with structs. So the pattern you just saw is the allocation of a memory segment, and you see that you have this arena object that we're going to talk about in a minute. And then you can use this with the set and get, providing a layout just tells you that, hey, I'm reading an int or I'm writing an int in that case. But we see that this layout API, this memory layout API, is actually much richer than that. You can also have an allocation on the heap. If you wrap a memory segment, you can wrap an array with a memory segment with this off-array method. This is what you just showed, Remi. So this is really a segment on the heap. So you can also use the memory segment API to read and write data on the heap. And you can also have it, and in that case, you are using the second access of the memory segment API, which is the array access, set at index and get at index. There is also this special processing for the string with the \0 at the end of it. And if you forget it, you will have a string that ends up with a bunch of zeros, which is usually not what you want. This is what we just saw with the ByteBuffer API, by the way. So you can easily do that with the ByteBuffer. And here are the patterns for the file mapping. So here it's just the same pattern as previously. So you're just wrapping an array with a memory segment. Then you are creating an off-heap segment with this allocate method. So the first memory segment is on the heap and the second one is off-heap. And then you copy the on-heap memory segment to the off-heap memory segment. Okay, so that's the first part. And then if you want to map it to a file, then you have you can reinterpret. So I'm not going to use this word. Okay, you can see this memory segment as a ByteBuffer, and then use this ByteBuffer with the traditional Java I/O file channel API to write it to the disk. All right. So as you can see, everything is quite simple and actually interacts very well with the ByteBuffer and the classical Java and I/O API. So you just saw different ways of dealing with this arena object. So we are going first to show it to you on your machine, Remi.
Yeah.
So I'm giving this cable once again. This arena object is actually the object that you are going to use to create memory segments. And this is the object also that is going to take care of the bookkeeping of memory segments and to close them as you are going to show it.
Yeah. So before we have seen that we can allocate a memory segment on a kind of a global immutable arena, but we have several kind of arena. The one you should use is of confine.
We're going to see why in a minute.
Yeah. So arena of confine, create an arena. In an arena, you can allocate several memory segments, and those memory segments can only be accessed by the thread that has created the arena. So it's as so basically all the memory segments like this one are bound to the thread that have created the arena. And then you can use it like a memory segment. It's exactly the same API, independent of the kind of arena. So you have this unconfined things, and here we have an example where we are trying to do some nasty things to the memory segment. So the first one, so let's run this, and in this case, so we create an arena, we create a memory segment, and then the first thing we will try to do is to access something which is far beyond the size of the memory arena, and in that case you get a nice index out of bound exception. So a memory segment will check that every access is in its bound, it's safe. The other thing you can do is this: is if you create another thread and try to access the memory segment, again, it will not work. You have I don't know if you know this exception, wrong thread exception. It's a new exception since Java 21. It was introduced by Loom. Loom is this kind of special method that are bound to a single thread. And so basically the off-confine mean the all memory segments created from that arena are confined to the thread that has created the arena. What you can so if you take a look here, because I'm using a try resources. Oh, sorry. Yes, you have a question. So the question is it possible to create arenas that are accessible by several threads? The answer is yes. And the second answer is you should not use it.
More precisely, we are going to talk about it so that you can understand the cost it has to do that.
So here's the question: in what if I'm setting a part of the memory segment after closing it? Basically, it's a use after free, and it
This is what we did with the ByteBuffer,
crash. Right? So, so you get an illegal state exception saying you are trying to access a memory segment which is already closed. So basically, an arena is a way to compound several memory segments, saying they are when you deallocate the arena, you deallocate all the memory segment at the same time. And it's not only for the set, even if you try to access with a get. Obviously, it should throw an exception too. So when you access to a memory segment, the size is check, the thread is check if you use off-confine, and you have a check that the arena is not closed. It's another demo to understand exactly what an arena is, because it's not what you think it is, sadly. It's more like a C things. I don't know if you know Zig, but it works like in Zig. But we will explain. So here I have an arena, and I create a new arena, and when I allocate things, I allocate the segment 1 in the arena 1, and the segment 2 in the arena 2, and the segment 3 in the arena 1. If you take a look to the address, you can see that the address are following one another, which means that when you allocate something in an arena, it's not allocated in a space dedicated to that arena. Basically, an arena is
there
just...
There is no space dedicated to an
arena.
arena.
There is no space dedicated to an arena. An arena is just a group of memory segments that should be deallocated at the same time. But it's a virtual thing. There is no memory specific to a memory arena, and I think it's... Okay, oh yeah, the cable.
The cable. So let us wrap up this and show exactly, see exactly how things are working. So basically, an arena is an object you can use to create off-heap memory segments. You cannot create on-heap memory segments in an arena because allocate gives you some piece of off-heap memory. It initializes the memory segment you have with zeros, and we're going to see that it has an impact on the performance, even if it's not very big. It is auto-closable, which means that it has a close method, and that if you use it in a try with resource statement, this close method will be executed when you exit the try block of this try with resources statement, even if there is an exception that has been thrown or if finally close. Okay, and this close method deallocates the memory segments. Now we're going to see that it's not always the case, and we are going to see the different types of arena. You have 4 factory methods on this arena class. The first one is the global arena. It's actually a singleton in your application, and it's never closed. So there is a close method, obviously, but this close method will not close your memory segments.
And throw an exception saying you are using it wrong.
Yeah. So if you use this arena, then the memory segment that you are going to create will be there forever. They actually share the life cycle of your application. So if you never close your application, this memory segment will never be closed. And then you have 2 arenas that you well, no, you showed the first one. The confined arena. It has a close method, and it will close the memory segments that it created when you call this close method. And this is the arena that checks what thread is actually accessing the memory segment it created. And it will only allow the thread that created this arena to access these memory segments. So these memory segments are confined to the thread that created this arena, right? I would say this should be your default choice because it's the cheapest way to create memory segments and to close them. Now the shared arena will allow for the access of several threads at the same time on your memory segment. But then it has a cost because when you close it, basically, it will close this memory segment, but it needs to check for all the threads that are there if they are done with their writing, their reading. And they also need to check, once the memory segment has been closed, for all the threads, it needs to check if they are trying to still access this memory segment. So this has a cost, and we're going to see it in the performance. There's a question?
Yeah.
Yeah. Does that mean that calling close on a shared arena will basically not return until all the threads are done with their reading? Or
You can repeat it.
Yeah,
please.
so the question is, does it mean that when the close method of a shared arena is called, it needs to, sorry, can you say that again?
Is it waiting on the other, like is it basically calling a join on all the other threads?
Oh, is it calling a join on all the other threads to wait for until they are done?
So yes, it's something like this. We will see exactly how it works.
More, yes.
It's just awful.
And the last one is the off auto, which is an arena that if you call close on off auto, it will not do anything.
No. It will throw an exception saying
sorry.
you are using it wrong.
It does not. It doesn't close the memory segment. This is what I meant. Why should you be using off auto? Never actually.
So off auto is legacy support. It's here because we want to retrofit ByteBuffer on top of the memory segment API. But it's not well named. It should not be called off auto. I mean, it's a too simple name. It should be called off legacy. Please don't use it. Because basically what you are saying is that you are waiting the GC and the GC will do the close. So it's not. It has exactly the same issue as the ByteBuffer, obviously, because it's the way to support ByteBuffer, but please don't use it. I mean, you can use it in your laptop, but not in production.
So these are the 4 arenas. They are all closable. They all have a close method, but you should not call the close method on all of them. The confined and shared and auto has a bounded lifetime, the memory segment, with the caveat that this bounded lifetime is not known in the auto case. It is known because when you call close, that's the end of it in a confined and shared arenas, but it's not the case for the auto. And the sharing of among threads is not supported by the confined one, which is the reason why it's the cheapest one to use, but it is supported on all the others. All right, here for some
benchmarks. Yes, to explain why you should use it one or the other. So what the benchmark does is just trying to do a get in a random place in memory. I think I use the location 12, so it's random.
12 is random, yes, absolutely.
And so the first bench is just I have an array of int and I am trying to access to one int inside.
So the first one is really a classical array access. Why?
Yeah, but it's not an array access. It's an array access.
Yeah.
Just one array access. So it's quite cheap. If you compare to unsafe, you can see that unsafe is a little faster because when you do an array access in Java, you have to check the bound, and you can see the cost of checking the bound for one access. And if you are using off-array, so off-array is you create a memory segment from an array in memory, you can see that the cost is far higher. No problem, we will explain how to alleviate that cost in a minute. And if you are using off-confine, off-auto, off-shared, or off-global, basically you have exactly the same kind of cost access. Why you have this kind of cost access? It's because you have to check the bounds, you have to check the thread, you have to check if it's closed or not. And technically, the cost that dominate is checking if it's closed or not. Because even if you have something that that cannot be closed, because you need to have exactly the same code for all of them to be correctly optimized, it means that you have to check that you cannot close. Anyway. And this is the same benchmark, but using a loop. And when you use a loop, the magic happens. Which is, if you take a look to the first line, this is looping on an array, a classical Java array. And if you compare to unsafe, it's exactly the same time. Why? Because since a long time, we have an optimization in the VM that removes the bound check if the VM can prove that you will not access outside of the bound. If you take a look to off-array, you see that it costs a little more, but what you cannot see because we haven't shown, but if you change the size, you will see that it's a fixed cost. Basically, you have a cost, but not inside the loop. You have a fixed cost at the beginning before the loop. And with the other memory segment, you can see that it's exactly the same cost, independent of the arena you are using. So basically, accessing a value if you have a loop is kind of great, actually. You don't have to use unsafe. You can use the safe things because the VM will be able to optimize. So we will, in the next slide, we will try to explain the overhead and how the VM is able to avoid them if you have loops. So the first thing you can see is that basically the access time is independent of the type of arena. You should not use a kind of arena expecting to have better performance in terms of access. The access is exactly the same, whatever the kind of arena that you are using. If you do a random direct access, the overhead can be quite important. It's basically you need to do three different checks. The first one is it the right thread? The second one is the arena is closed or not? And this is the one that costs you the most. And you have to do the bound checks. If you have a loop, basically you have a fixed cost at the beginning of the loop. Why? Because the VM will try to migrate all the check outside of the loop and doing it once and not every time you are in the loop. So this is something we call hoisting things, which is moving things from inside the loop to outside of the loop. So is it the right thread? It can be done once, and technically, usually it's not done because the VM already knows the thread you are running in it. I don't know if you know, but when you do a thread.current thread, the VM has tend to merge all this check into one at the top of the inlining horizon. I mean, in the VM, when you have several methods, the VM will collapse all the methods into one, inlining the whole thing, and you have only one check at the beginning of that big assembly blob. So it's checking a thread is it doesn't cost you much. Checking if the arena is closed as a cost, because from a memory segment you have to go to the arena, so you have to follow a pointer and then check the whole thing. Yes, there is again a question.
Because the arenas are auto-closable, if you are in the scope of the auto-closable thing, would it be possible for the JVM to go, oh, you're still in this scope, the arena can't possibly have been closed? Or do we expect people to just call close on arenas while you're in the scope, and that's why we have to keep checking?
So is there an optimization for the try resources? To my knowledge, no, because you cannot hope everyone to use a try resources. But you have an optimization, so it can be done in the future. I don't think it's done now. So no, the optimization is more around loops currently. And the last check is a bound check, and this one can be elided exactly the same way it works for classical Java arrays.
All right. What about we take a coffee break?
Yes.
I mean, do you think it's the right time to take a coffee break?
Is it?
Do you think it's the right time to take a coffee break?
Oh, not that.
Yeah, not that many.
Yeah.
Do you want to skip the coffee break?
Are sleeping.
No, very few people want to skip the coffee break. So just to give you a hint on what you're going to see after that, we're going to talk a little more about memory fragmentation and the impact it has on this stuff. And the rest of the presentation will be about a very hot topic currently in the OpenJDK and outside of it, which is called application integrity, and how the memory API is actually aligned with the integrity of your memory. We'll show you how you can use J-extract to move from your struct, so your C-struct, to a memory segment layout. We talked about structured memory access, VarHandle, and how you can use records to create a simple access API. So coffee break. Great. Let us start again in 15 minutes. Is it okay? 20?
Yeah. 20 minutes.
20, 15? Okay, let's say 20 at 11:05. Welcome back. Was the coffee nice? Yeah? Was the coffee nice? Oh, there are actually more people using Java 21 than people that had a coffee. So maybe the correlation in between both. I don't know. Can you, the people who are still working in Java 8, can you raise your hands again? No, they're not the same. So there's no correlation. I don't know. Okay. Never mind. All right. So we are back for about 1 hour and a half, which is great. That's plenty of time. I love it. So we were talking about arenas, the different types of arenas, and we showed you that the access time, whether it was random, that at a given index or at a given offset, or when you're looping on the content of a memory segment, actually the performance are very similar, very close to one another. from one arena to another. And even if you compare with the unsafe stuff, it's also very, very different. Now, this is not the only thing that you're doing with an arena. You need to understand that first an arena needs to create the object, and you also need to close it. And it is not something that does not take any time. So we like to talk about it now and show you the performance of allocation, deallocation of an arena plus a memory segment. And you can see that when you allocate an array, it's actually very fast. It's funny because an array, when you get an array in Java, this array is filled with zeros, and there's actually an optimization when a thread is not doing anything in the JVM will tell that thread, hey, you're not doing anything, takes your hands out of your pocket and go and put some zeros in this piece of memory, so that if someone needs it, then the zeros will always be there. So actually creating an array, allocating an array, is really very fast. What is the size of the array, by the way? We didn't put it on the slide.
500.
Yes, it's 512.
It's the same, yeah.
Yeah.
Size.
When you're doing off array, that is, you have this array and you create a segment on heap that is wrapping this array, it's actually longer because you need to create the memory segment object itself, right? And the difference between both is actually the creation of this memory segment object, which is also pretty fast. We're talking 4 nanoseconds, right? So it's not a lot. You can really create many, many memory segments in a short amount of time. But when you're using unsafe, which is doing a malloc, then you jump to 22 nanoseconds, which is a little more than 3 times slower, which is a lot. And when you do unsafe within it, that is with a bunch of zeros in this piece of memory, it's even higher because, well, you need to add the zeros to this off-heap memory. Okay, and when we have this arena of confined, then it's even higher than unsafe. Well, confined is the arena that actually doesn't check for multi-thread. It checks for multi-threaded, but it's not going to stop to check if another thread, to allow the access to multiple threads. It's the arena that you should be using. And you can see that the allocation is actually not something that is free, right? And the difference between off array that is on heap and all the other allocations that are off heap is actually finding a place in memory that is available and that will fit the size of the memory segment you need. So it's actually looking for some place because of fragmentation. So how is it working? It's working in that way. Suppose that you have 2 arenas. The first one is the green one, okay, and you just allocate a memory segment. And when you allocate the second memory segment, it's actually taken right after the first memory segment. This is one of the demos that you showed, Remi. But then if you have 2 competing arenas on the same off-heap memory, you create these 2 arenas, and then with the arena 2, you create a first memory segment, and then another memory segment with the other arena, and then another memory segment with the, here it's the second arena, actually, and then another memory segment with the first, and then another one with the second. This is the demo we showed you. This is what is happening in memory. All the memory segments are allocated just one after the other. And there is no difference from one arena to the other, because this is how the API is working. Actually, an arena is not, you cannot see that as a space that is reserved for you, and it will allocate memory segment from that space. An arena is just an object that is living on heap, of course, as all the objects in Java, right? And that is just pointing to memory segments that are also on heap, but that points themselves to contiguous pieces of memories that are off heap. Right. And now, suppose that arena.1 is closed. Okay, so you call this close method. The semantic is that all the memory segments that were reserved by that arena are going to be deallocated, and the corresponding memory becomes available. Okay, so this memory is gone. But then you have a third arena that is trying to allocate more memory segments. Well, there are 2 cases. The first case is, yes, this memory segment can fit in a hole that you created, so you can put it there. But as you can see, you are creating another hole that is smaller than the previous one. Okay, but if you want to allocate a memory segment that is bigger than any hole that you have, then you will create some fragmentation. Okay, so actually, every time you create a memory segment, there is an algorithm under the hood that is running, and that is asking, where can I put this memory segment? Where is there a hole that is big enough to accommodate for the memory segment that your code is asking for? And this has a cost, and this is the cost that you see when you're allocating. Okay. So you end up with holes in your memory, which leads to problems.
Yeah. So basically, the whole off-heap allocation in the memory segment is based on malloc. So you have exactly the same issue that you have usually with malloc. The thing is that because we are used to Java, we have not think about it a long time. But the first thing is that the allocation is slow. As José said, you need to find a big enough space to allocate things. And the other one is that you may have free memory, but you don't have enough contiguous free memory. So you will not be able to allocate something because, yes, you have free memory, but right in the middle you have an object. And then you have split your native memory in two. Which is a problem in itself. Okay, more benchmark. So off-confine, it's quite expensive, but it's far less expensive than using off-auto and off-shared. So why off-auto is expensive? Off-auto is expensive because this is a legacy implementation, and the legacy implementation do something quite, let's say, weird.
What is funny is that the error is plus or minus 250.
Take a look to the error.
So it means that actually when you're calling off-auto, you have, if you consider the distribution, it is between half a microsecond, right? And half a microsecond plus 3 times this. So that's almost 2 microseconds. It's 2 microseconds.
So this is
super slow.
This is mostly due to the cleaner API. When you call the cleaner API, you have a nice synchronized right in the middle. So it costs quite a lot, and it's even worse than that because you have a kind of if you have pressure on the native memory, you can even have a system.gc, which is called right in the middle of your allocation. So this is not the real cost, and this is why you have such variation in terms of performance, because you have a mechanism that try to rescue and do some things. When you have some memory pressure, you don't want to have an algorithm that try to be smart. You want to stop and just ask the user to have more memory. But it's not how it works, and because this is the semantics of ByteBuffer, we cannot change it. We cannot be smart now. We should have been smart 22 years ago. So this is off-auto. Remember legacy semantics?
But there's even worse.
And you have off-shared. And off-shared is, I think you can go to the slide. Yes. So off-auto is slow because this is the ByteBuffer semantics. It can call system.gc. Nobody should call system.gc in production, but this is exactly
we just did it in a demo. Was it okay?
Yeah. It's a demo. It's okay. So off-shared. So off-shared is really the kind of the jewel of the implementation, and at the same time, something that can cost a lot. The thing is, you have a memory segment that can be accessed by several threads, and you want to check if it's closed or not. If you have read at least the first pages of any concurrency book, the first thing is, if you have several access, you need a volatile access to check if one thread can see the change from another thread. But if you have a volatile access, each time you do a get, you're just dead. Basically, dead in the water. Yeah. How many people are using atomic integer to have mutable ints in their code?
Okay, so you stop doing that.
We should kill
now.
you. Because
come on.
oh no. I mean what you are asking to the
need to
CPUs, to the core, is just insane. The cost of a volatile access is just. I mean,
Okay,
you don't like your CPUs?
we're going to show you a pattern to avoid doing that.
So basically, get cannot do a volatile access. So this is a problem because any thread can close the arena. At the same time, another thread can access it. So what's the way to doing it? It's quite. I don't know if you know, but the GC have save point, which is inside the code. You have some part of the code where the GC can run. The GC cannot run everywhere in your code. Basically, you have to stop the thread at some point where you have enough bookkeeping for the GC to run. What we call a save point. Usually what you do in a save point is just a GC, and then the platform evolves and you start to do a lot of weird things inside the save point of the GC, like reclaiming the memory allocated for locks and things like this. And sometimes people see the code in production and say, oh, the GC is slow, and when you take a look, it's something which is run at a GC save point, but it has nothing to do with GC. So we are mod things into this GC save point, which is basically when you want to close a shared arena, you will ask all other platform thread to go to a GC save point. And at that time, you know that you are not running an access because you are at a GC save point. But GC save point can still occur inside a loop. So if it occurs inside a loop, you still have the issue that the close check, the check which is done because the arena can be closed, have been hoisted outside of the loop. So you need to ask the thread, take a look to your locals variable and check if there is not this arena on your locals. If you have this arena of your locals, I can throw an exception because I will not be able to close the arena because it's too dangerous. The code may access to the memory segment without a check because the check have been hoisted outside of the loop. So this is basically what the algorithm does. It stops all the thread, asks all the thread, are you on top of your stack? Are you doing an access to a memory segment? And then, so the way it's done, it's you tag every method that does memory access. This is what the JDK has done. And when you compile an inlining horizon into a method, you tag if somewhere you are accessing the memory segment. So you can you have a fast check to check if inside your assembly blob you have a memory access segment. If it's the case, then you take a look to all the locals and see if you have the arena that you want to close. And in that case, you will throw an exception. The main issue with that is that the algorithm is linear with the number of platform threads. So it will work in your laptop, and it will not work in production, basically, because you have 100 platform threads. It's not that rare to have a lot of cores. And so currently, the number you are seeing is running on my laptop, which has only 8 cores. So the number can be far bigger. So if you want to close a shared memory, I mean, the number is not that big. It's in microseconds. It's 10, usually 10 to 100 microseconds. So it's mostly like a call to the kernel. It's the same kind of ballpark, which means that you can only close a shared memory if you have a call to the kernel not far, because it will mask the cost of the shared things, which is great when you unmap a memory segment, because when you unmap a memory segment, you will do a call to the kernel. So in that case, you will not see the cost of closing the memory, the shared memory arena. But if in your program you're starting to use as a shared arena as something cheap, it will not be cheap at all. That's the main issue with. But it's interesting. It means that we have a way to solve the problem of being able to deallocate and at the same time allowing multiple threads to access without paying the cost at the access time. You paying it when you close the arena.
All right. We have demo.
Yeah. And I think.
So, yeah. Sorry.
Yeah. Go ahead.
This one, right? No, you did this one.
The next one.
All right. So what are we doing here? We are working with the arena of confine. By the way, you know that in Java you can write this kind of thing: var box equals new object. Okay, int index. Maybe you have a method void. Well, maybe I could, void inc index plus plus. That's an anonymous class, right? You remember anonymous classes before the time of lambdas? Okay, but outside of it, I have access to index. I could say index equal 1. Okay, and box dot inc. So all of you who are using atomic integers to write mutable boxes, now you can use that.
And guess what? It's far faster.
Oh yes, and you can pass.
And you can show your love to your CPUs.
If you have a collector, for instance, and you want to pass the first parameter of a collector, that is a supplier, you do a supplier with this stuff. Just add the supplier here, and as long as you don't put it in a supplier of something, it will keep this non-denoted denoted type, and you can pass it if you can get it again in the next lambda of your supplier, and still be able to use this in your code. Yeah.
I mean, we should have a mechanism that just roast you each time you use atomic integer.
All right. So what is this stuff doing? It's basically creating an arena of confine, and it's mapping this arena to a file. Okay. And this memory segment here, off array, is creating an array of bytes. It's getting the segment we read from the file. You see that, sorry, I'm going too fast here. You see that this file map is actually the file map from Java NIO, right? It's a file channel here, so this old object from Java 2. The map method was already there in Java 2, but now it's also taking an arena as a further parameter argument. So it's an overload of the classical map method that you've been using for 20 years. We've been using for 20 years. And now it returns a memory segment. So basically, the API is almost the same. It hasn't changed much. All you do is pass this arena to get a memory segment instead of a byte buffer, right? And so first, we're going to create an array segment on an array of bytes, right? So that's the on-heap memory segment that we've already created several times in the demo. And we are copying what has been read in this memory segment with this as a slice method. So we are just copying 10 elements from this memory segment into this array. Why? Because this is an array of 10 bytes, okay? And I can only copy 10 elements in an array of 10 bytes. That's quite logic. And now what I'm going to do is just print this as a string. So this is the constructor of the string class that takes an array of bytes as an argument. And this is the array segment. So the array segment is the on-heap segment, heap base or else a throw. So that's actually the array I'm using it. I could also write it in that way, by the way, putting this in a variable. This is my byte array. Okay, and just so this is a way of reading it as the array. But I could also, I'm going to keep this line here, but just put this there.
Yeah. From a memory segment, you can ask for the heap array.
Yes.
If you want.
By the way, what is it returning? It's just that it's not returning a byte array. This is what you have a cast. I guess so.
Yeah, because
That's
it's just an object.
Yes, it's just an object.
Because there is no superclass for all primitive array in Java,
Exactly.
for whatever reason.
So that's going to read so that's going to print. The string that I have here. I'm going to comment this and just to keep the heap base call, but it's basically doing the same. And you can also call on the segment there, so that the first pattern is this one, and you take the memory segment and you copy it. The second one is just you take a slice of this memory segment that you read from the file of the 10 elements, and you call toArray on it, passing the type of elements of the array you want. And here it's an array of bytes. So that's the array. It's an array, obviously, on heap, and then you can also print it as a string. So these are two patterns to read an array of bytes from a file, map it to a memory segment that is off heap, and transferring this memory segment, the content of this memory segment, to an array of bytes on heap, and making it a string, because why not? So if I run this code, here, it will also run this box here. I just closed the windows I wanted to show you. Okay, so now I just read the content of the file, and you can see that here, because it's a memory segment, you can still mutate the array through this memory segment. That by putting at the index 5 this character as a byte, which is a carriage return. So in the content you will have hello file mapping, and with the carriage return in the middle of it.
I think we should talk about the fourth method, which is when you write into a file which is mapped in memory, you don't have the when you read it from the file, you can get the old content, perhaps not the one you have updated. So you have to ask to sync as
it's like a flush.
Yeah, that's
kind of.
That's basically sync. That's the name of the
the system call.
Yes.
Okay. I'm going to jump directly to this memory, to this demo. So for now, we've seen two accessors to the content of a memory segment, which is the direct access. You want to access the byte at the offset 42, for instance. And the index access, you say, oh, this is a segment that contains integers, and I would like to access the third integer, for instance. So the set, get and get at index and set at index. These are the two methods that we saw. Here I'm going to create a memory segment of int.
A quite big one.
Okay, and now I'm going to put 4 billion ints in this memory segment. So we are going to create a big memory segment. Fortunately, this laptop has enough memory to arrange that. Okay, and now we are going to use another way to access this memory segment. Because you know how to access one element after another, you can put that in a loop. And by the way, this loop, you can index it with a longer instead of an int, even if it's not something you should be doing. But you can also use the stream API to directly stream the content of your memory segment. This is something I showed you on the very first demo at the beginning of the presentation. But now we are going to show it a little more precisely. So here I have this segment. I am telling that this segment is composed of integers. This value layout is just a way of saying, hey, this, yeah, just that.
This is an array of ints.
Yes, this is an array of int. And this element method here actually returns a stream from Java 8, right? So everybody knows what a stream is. And I'm going to map it to int. This S here is actually a segment. I'm going to
it's
call
a
it
slice.
memory segment.
Yeah, it's a slice of a segment.
So it's a stream of memory segment. Doing that splits your memory segment into slices of small memory segments that are going to only carry a Java int. That is 32 bits. And if you get the content of that, it will be interpreted as an int. But these slices are views on the memory segment, all right? It's not something that is that it does not copy your memory whatsoever. So from this memory segment, I'm using a get, which is the get that we already saw a million times.
Yes,
all right?
the direct access.
And because there's only one element here, I'm getting the get at the offset 0, knowing that it's a Java int. If I were to put 1 here, it would crash because I would be outside of this slice memory segment. And then I'm calling max because this is a map to int. So I have an int stream, and on the int stream I have a max call. And by the way, I'm going to call it or else a throw, so that I can open the optional I will have. And because this memory segment is obviously not empty, my optional cannot be empty neither. So I'm going to run that and measure the time it takes. And I can't remember the time it takes. I already did the demo, but I checked it. I think it was a little something like...
It's quite long. We can talk and...
Okay. Oh, it's 7 seconds. And the max is 0. Yes, because we put zeros in it. But we knew that beforehand, so why did we compute that? Just for the demo, right? But because it is a stream, I could go parallel on it, right? You're all using parallel stream, don't you?
You can compute 0 faster.
Yeah. So let me run that. And what do you think is going to happen, by the way? Ah, yes, exactly. Yeah. I'm going to get a wrong thread exception. Why? Because this parallel stream is actually creating, or it's not creating, the streams are already there. They are in a common function pool. But it's using actually the threads from the common function pool to access this memory segment. And this memory segment has been created with an arena of confined. And the arena of confined prevents other threads to access the memory segments it creates. So if I actually want to do that, I need to use an arena of shared. All right, so just be aware of that. Now if I'm running it, it will go much faster, and it will go in 1 second instead of how many? I can't remember. Should have checked. Okay.
It's faster. It was 7, I think.
It was 7. Yes, I think it was 7. I have so many cores on that subnet. No, I think I have 4.
Yeah, but
Well, whatever. It's faster. Never mind. Okay. So you have this way of accessing. If you want to stream the content of a memory segment, and odds are that you're going to do that a lot, you have this possibility of accessing it with the stream API, as long as you're using this layout here. And we're going to talk more about the MemoryLayout API. And this is really great, I think. I'm not going to talk about the legacy arena now, am I? Can't remember. Actually, yes. Okay, so let's go back to the IDE. Sorry for that. So the legacy arena of auto, you don't need to put it in a trial with a sources statement. It's just classical way of allocating, getting an index and everything. Okay, and what you said is that if I try to use it in a trial with a sources statement, I have an exception. Is it?
Yeah, at the end, yeah. When we call close, it will say.
So if
don't use it that way.
If you really want to do that, unsupported operation exception, because the close method of the arena of auto does not support close. So don't do it. By the way, it's the same for of global.
Yeah.
If I'm not mistaken.
It's global, not
sorry, global. So if I run it in that way also, and try to call it, it also throws an unsupported operation exception. But really, if you're writing some new code on with the memory API, of confined should be your first choice. Of shared, if you really need that, and it could be the case for parallel streams.
Yeah.
So is it the case then that to deallocate a memory segment, you have to close its arena? You can't just deallocate the memory segment. So anything you put in the global arena is perpetual.
Exactly. So the question is, you cannot. The question is about closing memory segment. You cannot close a memory segment with the memory segment API. You need to close the arena, and it will close all the memory segment that you've created. So if you create, so the answer is yes. If you create memory segment in a global or the auto arena, they will stay forever. They will share the life cycle of your application, because these arenas, the global arena is sharing the life cycle of your application. It's a singleton. There's only one in your application, and the auto is a new arena, but that you cannot close. So all the memory segments you create from there will not be closed. But the auto stuff is there for legacy reasons.
At some point, maybe the GC will decide to close that.
Yes,
maybe.
Or you can call a system.gc, which is, as you know, something you shouldn't be doing. All right, so let me go back to here. We're going to talk about memory integrity, by the way.
Okay.
So I don't know if you check very often the website of the White House. No, never go there. Well, it turns out that in February they published this article. Last February, so it's quite recent.
And and basically it says that you should stop to using C. It's not written that way, but if you don't have a memory safe language, you will have security issues. That's the main thing. If you take a look, one of the main attack vector is to use memory that after the memory being freed. So you should use a memory safe language. And guess what? Java is one.
Memory segments are safe.
By default. And even creating, you can create a memory segment from a long, because we want to have a C interrupt. So you can get a pointer along from C, and you can see it as a memory segment. It's a safe operation. Why? Because by default, if you create it from a long, the size of the memory segment will be 0. So it's safe. Yeah. You cannot use it for anything, but apart asking the byte size.
Don't forget to close it.
To close the arena. Yeah. And you have a special operation called reinterpret that can provide a size for a memory segment. And this method is unsafe. This is the only one in the whole API which is unsafe. Basically, you're opting in for saying, I know Java, I'm a wrong kid. This is a sin, but I want to be able to see any memory as a memory segment. And for if you do that, you should the VM requires you to use a flag called --enable -native -access. So you have to opt in for it. Technically, currently in Java 23, it's only a warning. But soon it will be an error. It will be an error at the same time it will be an error to use unsafe, basically. So the thing is, it's not the API of unsafe is not good. The memory segment provide another way to do unsafe things, because for a lot of software, it makes sense to interact with C and to do unsafe things. But it's easy to audit it. You have one call, which is reinterpret. So it's quite easy to have a static analysis that check if it's work or not, if the library will use something unsafe or not. And the other thing is that you need to ask the user of your library or the user of the application to opt in for this.
There's a JEP.
There's a JEP, which is a JEP that. So I don't know if you have seen this this move, but this is something which is which was started for in Java 9, which is basically tells the user of an application what exactly the application does, and not because what we have seen in the past a lot when we develop the module system is that people have no idea about what the libraries are using, or technically the library which is used by libraries are using. A dependency far, far, far from what you are seeing in your POM file is using, and we want people to be more aware of it, because the attack surface is very different if you have a library that do unsafe thingy or not. So that's all the JEP. And currently we are on the verge of having most of them starting to report errors when you use GNI or when you use unsafe and so on.
You have a demo, Remi?
Yes, I have one. Works. Yes.
Yes.
Yes. So I can have a memory segment. So the first thing is you can always access to the address of a memory segment. It's really great for debugging. And you have a method called off-address. And you can create a new memory segment from that long and just print it. So here you have the first segment, you have the address of the first segment, is this address. And here you have the new segment I have created with of address. And it creates a segment with a byte size of 0. And here I'm using reinterpret, saying now I want to set the size of this segment 2. And you can see all the warning saying, oh, you use it, but you have forgotten to use -- enable -native access. You can see that this flag take either all a name if you are not using modules, but you can, if you enable it and you have your dependencies in, if the dependencies are using a module, you have to explicitly say the module using. So you can segregate and see which library is using unsafe feature and the one that are not using it. The other thing is we have a segment called null that exists, and I will comment this one, and if I run it, oh, if I run it, you can see that a null segment is a segment at the address 0 with a byte size of 0. So obviously if you try to do a get on it, it will just throw an exception. So technically you can access the null segment. Not a long time.
It's only because it's not null, actually. It's not a null object, I mean.
It's not a null object, but it's a null segment. And if you try to access it, you will get an out-of-bound exception. This is how we simulate null from the Java side of things.
I have a question about this API here, or the combination of the of address and then reinterpret.
Yes.
Is there ever a reason you would use of address and then not reinterpret? And vice versa, would you ever reinterpret any other memory segment that you didn't get from of address? Like why are
Okay,
they
so
the same?
if I repeat the question is why using of address and have a safe memory segment I cannot access, and why not using reinterpret directly at the same time that I do of address. It's purely in terms of API. You can return a memory segment, and then the user can decide to use reinterpret or not. So at the, if you are writing a library that returns something from C, you can return it as a memory segment and then let the user do the unsafe things. You don't have, as the one calling C, have to do the unsafe things. That's basically the idea.
And then the other way, right, if you have any other memory segment, not one you created from an address, and you call reinterpret on it,
Yes.
what happens?
You should not, because you have slice.
You need to repeat the
Oh,
question.
yes, repeating the question. You have already an existing memory segment and you call reinterpret on it to create a new one. So the answer is you have slice for that, and slice is safe. You should not using reinterpret on something.
Yeah, but does it throw or does it just go?
That's a really good question. I have no idea if it, but we can test if it's the case or not, which is I will use segment here, which is one I have allocated. And we can run and see what's happened. Oh, and I have to remove those things in the middle. And you can do it.
So basically, you What you did is that you allocated a memory segment of 64 bytes, and you can reinterpret it as 128 bytes.
Yes.
And then
But it's
odds are that you'll
saying
be in
you are
trouble
doing
at some
something
point.
unsafe. But you can, actually.
A much larger foot gun than the foot gun we already have.
So the comment was, we now have a much larger foot gun than the foot gun we already have. I
Yeah,
like
but
your comment.
you have
actually.
we
Thank
have
you.
only one foot gun, which is reinterpret. But yet, when you ask to reinterpret, guess what? It reinterpret.
This is what you asked for, right? I done?
Yeah. Yeah, sorry.
Could you reinterpret an on-heap stuff?
You can reinterpret an on-heap stuff and
That's
corrupt the on-heap memory
That would
if
be
you
so
want. Because guess what? When it's unsafe, it's unsafe.
All right. So we covered arenas and memory segment. We are going to talk about memory layout. And to talk about it, let me try it again. Oops.
It seems the presentation is finished. Okay, it works.
Great. And to talk about it, so let me do that again. We're going to talk about the memory layout API, which is the next part of this memory API. And for that, we're going to use a tool called J-extract, and we're going to talk about it also. And now it's my clicker that is not working. Good. So the goal of J-extract is actually broader than what we're going to use here, because we're talking about the memory API, which is a subset of the foreign function and memory API. And J-extract is used both for the foreign function part and the memory API and the memory part. And we are going to focus only on the memory part. So basically, J-extract takes a .h file that describes a C library, and it can create Java classes from it. That the classes is going to create is one class for each .h file that you give to J-extract, and then because we are only talking about the structs defined in this file, one Java class per struct that you have in this file. So if you have two structs in a single .h file, that will be three Java classes. These classes have the name of the structs that you have and the name of the .h file that you have. So they usually do not follow the naming convention of the classical Java classes. You may have a class that is called point_h, and this is the example that we are going to show you. Internally, it uses LLVM to parse the C declaration, and also to take into account the operating system specifics of the .h file. For instance, in the example that we have a short that is defined in a struct, but the short in C is 8 bits, so it does not map to the short that you have in Java, which is obviously 16 bits. So this kind of thing is taken into account by J-extract. That being said, when you download a JDK distribution and you have all this set of tools that you have in it, J-extract is not part of them. It's a separate download. It was on the one of the first slides I showed you was the JDK Java.net page, where you have the early access versions of several builds of the JDK projects, or the open JDK projects. And among these, you have J-extract, and J-extract is currently in version 22. Which generates Java 22 code, but it's okay because Java 23 is compatible with 22. 23 can run and compile and run Java 22 code.
Yeah, it's not a preview feature, so
no, it's not
there
a
is
preview
no
feature.
issue.
Absolutely. So we are going to use J-extract to create layouts, and the memory layout API is actually structured in that way. You have this memory layout interface. All these are interfaces. And if you just check the leaves, you have the struct layout, which we are going to use most because this is what lets you map C structs in memory, and value layout that you actually already saw, when you saw value layout.java int or Java byte that we used in these examples. And the padding layout is also used because at some point, if you want to respect the correct alignment of the elements of your structs, you will need to use the padding layout to align the bytes and ints correctly in memory. So how is a layout defined? Well, that's an example. That's a MemoryLayout.struct layout. So you have a factory method on the interface, and you just defined two value layout Java ints. So that's actually a struct that is made of two ints. So it could be a point layout, for instance. If you define your layout in that way, then you will need to access the different components of your struct, I would say by hand, right? You have the byte size of this point layout, and if you want to compute the offset that takes you to the first component of this layout, it's the point layout dot byte offset 0. And if you want to access the second one, you will need to call point layout dot byte offset, and then because Java int is on 4 bytes, you need to pass 4 as an argument. By the way, you could also pass value layout Java int.
1.
Byte offset. It's 1?
It's 1.
Okay.
It's return a byte offset. It doesn't take a byte offset.
Yeah, so it's one component.
Yes.
And that's not very convenient because you're doing everything by hand, computing your offset by hand. And by the way, I got it wrong, so, because I never use it. Because actually, the APIs gives you a very super useful feature, which is naming the components of your elements. Now here, I just added with name X, with name Y, and even the point itself can be named with name points. And now you can access, instead of accessing the byte offsets of the different components by passing the index of this component, you can give the name of this component, and it will take automatically the name that you put in your declaration to compute this offset. So it's obviously much better to do that. Now, here you don't have any problem because you have two ints, so you don't have any alignment problem. You can have alignment issues, and this is why you need a padding. Here we have a struct in C. The first element is a char, so the char in C is 8 bits. And then an int, which is called payload, and then another char, which is also 8 bits. You see, and you need to pad that in memory. So the first blue element is the kind. Then you need to have 3 bytes of padding to properly align the payload that needs to be aligned with an address that is divisible by 4.
Because it's an int.
Yeah, because it's an int. We saw that at the beginning of the presentation. And it's the same for the extra, the last character. And if you want to align your struct, if you want to have an array of such structs, of course the next struct that you are going to put in your memory cannot be aligned after this the extra component. It has to be aligned properly on the next divisible by 2, divisible by 4 address. So you also need to add some padding after
at the end. Yeah.
At the end.
Usually you think about the padding in the middle, but you forget the padding at the end.
At the end, but if you don't put it in an array, that will be probably okay. But odds are that you are going to put it in an array. And this is why you need the padding layout. Okay, so that's the struct layout that maps this struct. You have the Java byte, because a char is actually a byte in Java, with name kind, and then a padding layout of 3 bytes, and then an int with the name payload, and then a byte with the name extra, and then a last padding with the name 3. Now, if you want to play with this API, I really encourage you to do that, to do so with the Java, the JDK 23, because the JDK 22 is not great at giving you errors, especially when you have your padding wrong. Basically, it doesn't work.
Yes.
It doesn't create your padding. It can crash your application, but with no exception.
So when you call struct layout there is a check that the current CPU is able to use the current padding. Yeah. But the error was not reported correctly with Java 22.
Well, it's not reported at all. So
It's more weird than that.
okay, so 23. Use 23 and you'll be fine. And we have a demo for that. Yeah. So that's the demo I would like to show you. And I'm not going to run JExtract because there's really no need to do that. We have a nice library.h library, okay, with two structs, a point and a data, and we already run JExtract on it. And it gives you, so 3 classes. The first class is called library_h, which is not really following the Java naming convention. This is what I was telling you. There is a bunch of methods in it. We're not going to go through all this. And if you check, for instance, the point stuff, then you have this layout that has been created automatically by JExtract, which is basically the layout that we just saw. It uses this C_int here, which is actually mapped to Java int. Plus, it has a number of methods to return this layout and do some other things. So the code is here. First, I'm printing the layout of this point, then create an arena of confined. So that's the default arena you should be using. And then you can create, using this layout, a segment just to be able to hold a single instance of this point. And then the ext, so yes, this is actually the class, right? This point here is actually the class that was generated by JExtract. If I control-click on it, that's the class. It's very confusing because we're not used to having classes that start with a lowercase character, but here that's the case. So the X method is actually a static method that was generated by JExtract, and it's really great because it's actually doing the layout.set for you, but you only use it through an accessor-like, with an accessor-like pattern. You pass the segment and just pass the value you want to put in this segment, and it will just do the rest. And the second pattern is about allocating an array. And once again, this is a static method of the point class, all right, that was generated by JExtract. And it generates an array within that arena of 16 elements. That's a long, so if you want really many point elements, you can. And it actually returns, is it an array or a memory segment? No, it's a memory segment. It creates a memory segment that can hold 16 elements. And that you can use either as a stream, as we just saw, or with the different API. So here you slice this array because you also have an asSlice method that will just create a memory segment on a single occurrence of this struct. Okay, it will be the second here, and you can, if you pass this segment there, then what this line is basically doing, that is setting the X component of this point, which is the second in the array, to the value of 42. Okay, and here is the pattern with the for loop. You can just run that, and you can see that it's working as expected. So basically, it's really about putting together all the elements that we saw using this MemoryLayout API. So here it's the same. Oh yeah, I didn't show that to you, but I can show it here. So here on this stuff, it's just, where is it creating this this warning?
Oh, because you're using GExtract, and GExtract use reinterpret
right.
in the static init of the hash library you are using.
You can actually remove it from the class it generated because it's not doing anything.
Yes.
But never mind. So that's the data layout. Okay, so that's the other struct. I could put the point layout if you want here. So you see that it's a class. So here it's printing. Let me print that again. It's printing in this kind of weird string of character. It's actually printing the layout. This is the toString method of the struct layout that you have. So it tells me that I have an integer of 4 bytes, and this integer is called x. Then another integer of 4 bytes called y, sorry, Greek y, and all this struct is called point. Okay, this is what it tells me, and the size of tells me that it's holding 8 bytes in memory. And if I do the same, it was data. So if I do the same with data, it's a little more complex. I can show you data again. Data is actually let me show it to you here. So data, it's this one. So you see, you have a byte, one byte of size 1 byte precisely, called kind. Then a payload of 3 bytes. Then an integer of 4 bytes called payload. Then B1, which is
the extra.
extra, sorry, yeah, 1 byte called extra. Then 3
padding.
bytes of padding. And it's all called data, and the overall size is 12. So you can also debug your layout if you want with this kind of thing.
But it's very specific to the way you print layout. It's not something you will find anywhere else. It's just in Java the way you print the layout with this weird string format.
You can also create your layouts by hand, which is the case here. You see, now you need to be careful. It's a little like VarHandle. You absolutely need to put them in private or public static final members, so that JVM can.
It's something we will see later. But if your constant is not a constant, the VM will not optimize it as a constant, and will just give up optimizing anything.
So if I comment this line, then I'm messing up with the element. My data will not be properly aligned. Illegal argument exception, illegal element constraint for member layout, blah, blah, blah. So don't do that. Okay. And if I don't add this padding here, I would be so happy if I had an exception, but I don't think I will have one. Now it's working, and now it's really embarrassing because you will have a runtime exception if you try to create an array with this layout. So you need
But only when you access.
Only when you access, when you do sets or gets, because then the misalignment will be only checked at that time. So you just need to be aware of that. You need to know what you're doing with this kind of thing. And then this is about playing with offsets. So here I have this data layout, which is the data we just saw. We are putting it in an arena, and we are just accessing it using the offset. So this is a pattern that we actually also saw earlier.
So if you play with offset, you have to do what the C compiler does by hand, basically.
Yeah.
You compute the offset of each, and you multiply by the size of the thing, and plus the offset to access.
Actually, what you can do if you want to write this kind of code in a safe way is write a quick struct, which is super simple, like this, for instance, and put it in a .h. Sorry, like this. Put it in a .h. Put it in a .h file. Use JExtract to generate that, and then from the file that you have here, this group layout, you can just copy paste this and put it in your code if you don't want to use JExtract. Well, if you don't want to use the classes generated for you by JExtract to generate that. This is also a solution. Yeah, question?
Yes. So that's why you have C-int here, because the definition of C-int will be different depending on which platform you run GExtract.
So if I build a jet file on Windows,
it's
run that on Linux,
yeah.
it can crash.
Yes.
Yeah.
Welcome to the C world.
And if you want it to crash, you can generate something on a Raspberry Pi, on a 32 bits Raspberry Pi, or on a 16-bit Z80, if you have access to old machines. and try to run it on a Windows machine. Yeah. which is expected, by the way. All right. So I think I'm done with this demo,
Yeah.
right? Let me go back to the slides.
But yes, that's one of the main issue with G-extract, which is now you are in the C world and you need to target all your OSs you want to target and generate for each one.
You maybe saw that actually in the JExtract generated files, you had memory layouts on these kind of elements, but you also had VarHandles that were...
No, you don't have it.
Oh yes, no, you don't have it. You only have the offset stuff.
At some point in the past, you had it, but now... so you have two ways to access to data in when you have a layout. You can access by computing by hand the offset, and the other way is to use a VarHandle. So a VarHandle is just a way to hide the computation of the offset with a twist, which is the VM knows a VarHandle and is able to optimize because of that, and because a memory segment has a size. If you try to compute using offset, you will have a lot of bound check. And if you use a VarHandle, magically, all the bound check will disappear. Technically, with a VarHandle, you can ask for not only plain access, which is basically a get, but you can ask for volatile access or opaque things and fix them. How many people know the opaque access? Yes,
No one.
That's great.
0 people.
Forget about it. That's you should use volatile, not opaque.
You have a
That's
demo
nice
one.
if you don't use that access. So this is a demo on how to create a VarHandle. So I have my data layout, and I will create a VarHandle on it. So it's data layout.varhandle. Fuck you. And here, when you want to access to a VarHandle, you can use the name that you were using it here to directly say, I want to access to the field name kind. It's quite verbose, but you can just do a static import and it's a little better. And so here I am creating a VarHandle, and I can using either get or set. When I access to some data, so there are several things. First, if you do something and you ask, the VarHandle API is not that nice. Basically, the VarHandle API is saying, compiler, compile whatever you want, the VM will check at runtime. So if you do something stupid like adding 12 here, it will still compile, and at runtime you will have weird exception because this is the pattern that you should use. Here you have the memory segment. The second value is the offset if you are using a struct inside a struct. But here it will be 0 because we are not using a struct inside a struct. And then because this is a set method, the value you want to set. So here I want to set the value of the field kind, like I do exactly the same way with get here. And if I run it, it runs, but there is performance issue that you cannot see, which is because the API trusts the compiler, or because the compiler doesn't verify the API, because it's the same API if you access to int or if you access to long and so on. You have only one method, and the VM will figure out the type magically. But this is an issue because the compiler have no signature. So if you, here I have a bug because I do a get, and here the compiler will say the return value is object. So here I have an hidden boxing issue here. Obviously, everybody have seen it. So you have a way to say, please don't do any boxing, which is when you create a VarHandle, you say, please don't do any adaptation of it. So in that case, when you run it, it will crash and say, this is a wrong method type exception. So instead of having performance issue, now you can fix your code. But it's stupid. It's at runtime and not at compile time. So IntelliJ have you have exactly the same issue with method handle, and for method handle, IntelliJ is able to help you. But currently there is no help for VarHandle. I think the API is a little too young, and not enough people have bug IntelliJ to implement something. So currently you are on your own, and you have to say, hey, here, I want to return a byte. Because when I access and when I store it, it has to be a byte. And in that case, if you have returned the type correctly, then it's fast. So sadly, when you create a VarHandle, it's not with the invoke exact behavior by default. It should have been the default. But because when you create a VarHandle everywhere else, it's always the same semantics. So that's why this semantics was chosen. I don't know if you write concurrency code using VarHandles, but you have exactly the same issue, in fact. And this is how you can access to an array of struct. You can access to a struct, but you can also access to an array of struct. When you create from your layout, you have array element VarHandle, which means that you want to access to an array of struct. Here I want to access to the payload. I will say with invoke exact behavior, and in that case, I will pass a memory segment. Again, a 0 if the array is inside a struct. I will have to pass the offset. And then I can pass the index and then the value, the corresponding value. Again, because it's with the invoke exact syntax, I have to cast here my int to a long, because all index are long in the API. So it's a fairly low level API. Let's say really low level API. It can bite you in the ass if you don't care, if you are not. I mean, at least if you are using this, you will get an error at runtime and you can fix it. But don't forget it. And yeah, I think we can.
I need your
switch off.
AV cable.
So yeah, that's the main two issue with the VarHandle API. The compiler don't do any type checking. You have to do it in your head, or use with invoke exact behavior when you create your VarHandle and debug the runtime error when it comes. But using a VarHandle is very important because if you take a look to this benchmark, so we are benchmarking using an on-heap array wrap into a method memory segment and accessing it using either an offset or VarHandle. The same thing using unsafe and with an arena, whatever the arena, it's exactly again when you access something with an arena, it's the performance are independent of the kind of arena. And you can see in green that basically accessing a structure struct using a VarHandle is really, really close to the unsafe access. Again, you have a fixed cost when you do your loop. And using offset, it's like saying to the JIT, oh, you are on your own. I will not provide you a structured access to it. I will not separate what is an index and what is an offset. You are on your own. So yeah, you cannot. So basically, you cannot offset calculation like you do in C. You have to use the VarHandle API, even if the VarHandle API is not the best API to interact with it. Technically, it's a little more. One problem with the VarHandle API, another one, is that it relies heavily on the JIT. So the time to a steady run is quite long. So if you have a lot of VarHandle, you need to reach C2. You need to ask the best JIT to generate the right code. So it takes some time to reach that point. So if you are using micro benchmarking like GMH, it's cool, but in your application, it will take times until you reach that point. And if you are doing something like I put some data in a struct and calling a C function, it may not worth to create a VarHandle for it, especially if you don't do a lot of call to that C function. That's why you have both APIs, the offset API and the VarHandle API. By default, G-extract doesn't create the VarHandle, obviously to avoid the cost for the JIT by default. And so you have to create VarHandle if you want to have a faster access, because G-extract doesn't know if you will call this, if you use this struct once or several times. So the default is, it will take more time, but you have less metadata, it will be faster if you do only few calls on it. So this is currently, we have finished describing how the memory API is working, and currently now we are talking about possible future of the API. As you can see, with using VarHandle, this is not the best API to use, and we want to simplify it. One way to simplify it is to use record as a temporary moving object, which is you fill a record, you push it, and it will be written in the data structure, and magically the VM will optimize, and it will be cool. That's technically it works only if the VM is able to see the creation of a record and the last use of a record. Exactly, it rely on escape analysis, so it only works if you're using a record as a temporary object to write things inside a struct, and not something that you will keep using it. With Valhalla, it will be easier because you will be able to declare a value record, and it will be automatically optimized, which will be easier to. You will have stronger guarantee. So I think I have a demo of it.
You think you have the time?
3 minutes, yeah, lot of time. And I have to relaunch my IntelliJ because it just crashed.
Oh. I have it here if you want.
Yeah, you can perhaps show it. It will be easier.
We could have saved on this one. Is it a record mapper API?
Yeah.
Here you go.
So this is not an hypothetical API. This is currently what is discussed on the Panama mailing list. And so if you...
Sorry.
Yes. Yeah. So here, basically what you do is here you declare a record. It doesn't have to contain all the fields, only the one you want to update. So here I want to only update the payload of my struct. And so I will declare a record, and I will have a record mapper that works like Jackson. Basically the same kind of automatically mapping things. And here I will be able to use set at index and get at index and return a record or take a record as parameter, and magically everything will work, and it will be fast, because basically what the mapper does is for a record creates the correct VarHandle to use it, but it's fully hidden from the user. So this is something we want to add in Java 24. Maybe it will be in 25, but it will be soon. I think we have finished our presentation. I think if you have questions, it's better if you come to ask questions, because there is no time anymore.
Oh, I don't have anything on my screen anymore.
Oh.
And there's this one that
yeah.
is black.
Thank you to stay with us.
Okay, so that's, yes, I think that's the end, and we are out of time. So just the last message. Use Panama, is really a great API. We all hope that you like the presentation. You can already download the slides, because we were organized this year. So if you scan this QR code, you will have the PDF of the slides. The demo is not on GitHub yet. But
we have half organized.
Yes.
You have the slides.
You have the slides, and the video will be published tomorrow. So if you want to rewatch the video, you will be able to do that. Thank you, everyone, for coming to listen to us, and have a great rest of Devox.
All systems are nominal. Initialize Genesis sequence.